Some of the most fundamental chemical reactions on our planet, everything from what happens inside our own cells to the vast chemistry of the oceans, well, they all happen when things get mixed together. So today, we're going to dive in and break down the amazing chemistry of solutions and acids.
Okay, so here's a fun one to start us off. I want you to really think about this for a second. We've got a gas, a massive body of liquid, and a solid metal instrument. On the surface, they couldn't be more different. But chemically speaking, they share something fundamental. What could it possibly be?
You guessed it, they are all solutions. And this concept, it's way bigger than just stirring some sugar into your tea. It's a core principle of how matter itself comes together and mixes. So here's our game plan for today. We're going to start with the universal mix to see what makes these things tick. Then we'll look at their electric personality. Yeah, some of them conduct electricity. We'll find out what happens when you're reaching the limit, and then we'll get into their famous cousins, acids and bases, and finish with the great proton exchange. All right, first things first, let's get the absolute basics down. What is it that actually makes something a solution? The magic word here is homogeneous. All that means is that the mixture is perfectly, totally uniform. Think about it. Once you stir salt into water, you can't just pick out the salty bits anymore, right? Every single drop of that water is now equally salty. And every one of these solutions has two key players. First, you've got the solvent. This is the main component, the boss of the mixture. It's the thing that does the dissolving. In our saltwater example, water is the solvent because, well, there's a lot more of it. And the other player is the solute. That's the stuff that gets dissolved into the solvent. So in this case, the salt is our solute. Simple, right? The solvent does the dissolving and the solute gets dissolved.
Okay, now here's where we need to break a super common myth. Solutions are not just liquids. The air you're breathing right now, it's a gaseous solution, mostly nitrogen gas acting as the solvent for oxygen and other stuff. A brass instrument, that's a solid solution of zinc dissolved in copper. And by the way, anytime water's the solvent, we give it a special name, an aqueous solution.
So, building on that, some of these solutions have a pretty shocking ability. I mean, literally, they can conduct electricity. But how? Well, it all comes down to what the solute does the moment it dissolves.
We can basically sort all solutions into three categories based on this electric personality. A strong electrolyte is a solute that when it dissolves completely breaks apart, or dissociates into charged particles called ions, and those free-floating ions are what allow electricity to just flow right through. This is absolutely critical. It's how our nerve cells fire. Then you've got a weak electrolyte, which only breaks apart a little bit. And finally, a non-electrolyte. Dissolves, but it doesn't create any ions at all, so electricity hits a dead end. Let's make this feel a bit more real. Good old table salt, sodium chloride, is a classic strong electrolyte. Acetic acid, the main ingredient in vinegar, is a weak one. And sugar? Sugar is a perfect example of a non-electrolyte. You can dissolve a whole bunch of it in water, but that water still won't conduct a single spark of electricity. Okay, so imagine you're making a glass of iced tea. You add a spoonful of sugar, you stir, and poof, it disappears. You add another one, and it disappears too. But then, eventually, you hit a wall. You add one more spoonful, and it just swirls around and sinks to the bottom. Every solution has a limit. This whole process actually plays out in three distinct stages. At first, your tea is unsaturated. There's still plenty of room at the end for more sugar. When you've dissolved the absolute maximum amount it can possibly hold, we say it's saturated. But then there's this weird, kind of magical third state. If you carefully heat the solution, dissolve even more sugar, and then let it cool down very gently, you can create a supersaturated solution. It's super unstable, and just one tiny disturbance can make all that extra sugar crystallize out in an instant. So here's the crucial thing. That limit isn't just random. It's a specific, measurable property called solubility. It's the exact amount of solute you need to make a perfectly saturated solution at a specific temperature. Think of it like the official rulebook for dissolving. Now, this whole idea of things dissolving in water is the perfect bridge to talking about another one of chemistry's most famous pairs, acids and bases. And what's really fascinating is that our scientific understanding of them has actually evolved quite a bit over time.
So the first big theory came from a scientist named Arrhenius, and his definition is very straightforward. He basically said, look, if you dissolve something in water and it produces hydrogen ions, that's H+, it's an acid. And if it produces hydroxide ions, that's OH-, it's a base. Clean and simple.
And don't get me wrong, the Arrhenius definition was a fantastic start. It explains a ton of common acids and bases that we work with all the time. But it has one really big limitation. It only works for reactions that are happening in water. Science needed a broader, more universal definition.
And that brings us to the Bronsted-Lowry theory. Now, this is a much more elegant and powerful way to look at it. It doesn't focus on what a substance produces, but on what it does during a reaction. In this view, an acid is simply a proton donor, and a proton is just a hydrogen ion, that H+. A base, then, is a proton acceptor. It's really just a dance of donating and accepting a proton.
So let's actually watch this proton exchange in action. This is where the beauty of the Bronsted-Lowry definition really shines.
Okay, take a look at this reaction right here. We've got hydrochloric acid, or HCl, reacting with water, H2O. Now just watch that proton, the H+. The HCl molecule literally gives its proton away to the water molecule. It's a clean handoff. The HCl is left as just a chloride ion, Cl-, and the water, having accepted the proton, becomes H3O+.
So, based on what we just saw, that little game of proton catch, let's think about it. Who was the donor? Who was the acceptor? In other words, who acted as the acid and who acted as the base?
Exactly. Because HCl donated the proton, it's our Bronsted-Lowry acid. And because the water molecule accepted that proton, it was acting as the Bronsted-Lowry base in the specific reaction.
And this reveals something absolutely amazing about water. In that last example, it acted as a base, but in other reactions, it can do the opposite and act as an acid, donating one of its own protons. Any substance that can switch hit like this, that can be both an acid and a base, is called amphoteric. Water is the ultimate chemical chameleon.
So, I'll leave you with this final thought to chew on. If water molecules can both give and receive protons, what do you think is actually happening in a simple glass of pure water, where billions and billions of water molecules are constantly bumping into each other? What does that imply about the very nature of water itself?